Thank you. Thank you. So
But your
I have been
presentation is
associated with the.
not your presentation is not visible right now.
Okay, just a second.
I think you have to open the presentation, keep it on desktop,
Yes.
and then again go for screen sharing.
So I am sharing the screen. Hope it is. I'll put it on screen share. Yeah.
Yes, now it is visible.
Can you see the screen? Yeah.
Yes, yes.
Okay. Yes. So I've been associated with metal industry, treatment industry for the last 9 years approx. Have been working with the inoculation technician. Currently working with Elgum as a technical and art manager, located in Nagpur. Working with the foundry partners, the customers in India, and also working with the R&D center we have in North. So we will start. I mean, to talk about the inoculation, if you look at the context of it, it is like adding salt to your vegetable that we are preparing. So, I mean, it is an important part of which adds on to the taste. More of it is bad. If you don't add salt to your vegetable, it is bad. You do need some amount of salt, and of course the addition rate is very less. You add only a small bit of it, like we do for inoculation. We only add about 0.1, 0.2, 0.5, 0.6 approximately. So that's kind of how we look at inoculation it comes to metal treatment. The session will have the content. We'll talk initially about the gray caster nucleation, tiger nucleation, some bit magnesium. I will not go because magnesium is something is not of today's session. Without inoculation, elements, inoculation fade, impact, affect application of different elements. Thanks to Mr. Manish, who has already talked a bit about it. Some of the common myths which are related to inoculation in the phrase, we'll bust them today. To start, what is nucleation? Nucleation is something which we always talk about. We might cut it into a sense of casting. So nucleation comes as a factor. We want to convert the phase of the molten metal into a solid, and we do it starting from a crystal, from a very small from these nucleating gates. These crystals, which are the original nucleating sites, have their presence in this metal that happens even before inoculation. And of course, to have a very mechanical properties, very good material properties, to have sound casting where we don't have shrinkages or defect, we want to improve this nucleating nucleating presence in the metal, and that is why we add inoculant, or that is why we add an additive to it. Inoculation has been a very controversial one because right at the start, it was sodium silicate sand particles which acted as inoculants because they had the silica sand acted as a inoculant. They were the first inoculants which were used almost 100 or 120 years back. And then we gradually improved upon the of inoculation. Of course, the criticality of the casting and the requirements of the casting also improved with time. The grades became much more stringent, quality became much more demanding from the end users, the OEMs. That is how gradual growth in the quality of inoculant happened also took place with time. Today, we're talking about all the inoculant cerium in it with rare earths, with calcium, barium, zirconium, manganese, etc. But it's started with very silly to begin with.
Mr. Kumar,
The main
can you,
inoculation is very good.
Mr. Kumar, can you switch off your video so that network will be a little better?
Sure. Okay, so I think screen is visible. I can continue. Can you hear me?
Yes, sir. Go ahead.
Yeah, thank you. What started has become to a more fancy enough today, and the role of inoculants has always been to promote graphite growth, to ensure that when we have in excess beyond the solid solubility of carbon in iron, whatever excess carbon we have or carbon per se, convert to a graphite form. Want to be of carbide, that of only no. So that's the main of an opt. This is about, I will not with more of theory. Gray cast take and gray cast theory again is a critical one. We have oxide element and element, which is depict X as the if any foundry is using ferrocene as an agent and getting some benefits, that only because of the calcium internet. So there's no calcium will act as an so as such is not an inoculant. Should ideally not be used as an inoculant because it will always give inconsistent results. We have seen this graph for this is a type graph like formed in iron, and the impact of inoculation, which reduces the undercooling in the temperature which you see after this graphite precipitation, the eutectic graphite precipitation starts. As a tries to reduce dip in temperature, sure take graphite for the properties start hitting much higher. And the cooling very high, you will either type B or a E microstructure, or in worst get I carbide. The factor of a right inoculant history and the proper size, we have seen it slide. Consider the section thickness of the casting. That helps control the course of the fight break, which the strontium is in the heavy section, and that is the we always using strontium.
Everyone, I see a very good response to the webinar. Almost 90 people had joined, and I thank Mr. Sandeep Kulkarni and the Dynamic Foundry Group for this excellent arrangements. And thank you also for providing me this opportunity. And I'm Nadimuthu. I am the Executive Director of Marketing and R&D of SNAM Alloys. And SNAM Alloys has been in this ferroalloy business since 1987. And with just this small introduction and a warm welcome and thanks to all the co-panelists who have been, putting forward their views on the inoculant. So let me start the share screening on the topic that I have for today. It is the frequently asked questions. So what that we have seen, or what would the foundry men, come up with? What sort of, questions would they have? So I hope my audio is audible and you're able to see the screen completely.
It's perfect. It's perfect.
Okay, thank you. Thank you. So let me proceed then. So I will go over, I have selected around 12 questions. Of course, not exhaustive because the foundryman, you face plenty of issues. Mr. Manish Patrikar has also, briefed you that, we have to look inward first, look at the process and the solutions that come from these are, like the salt that Mr. Kumar said, So it's all the ingredients together that form a good casting. But we have these questions, so, they keep popping up. So what is the purpose of inoculation? The main purpose of inoculation is to reduce undercooling and thereby provide uniform nucleation through the casting. The uniform nucleation ensures uniform graphitization. Now, all the terminology, just to tell you, if you go into YouTube and look at undercooling of water, water is supposed to freeze at 0 degrees and form ice. If you're keeping it in a still temperature, even at 4 degrees, it does not form ice. You just tap it and you will see that it suddenly freezes. So the same thing, undercooling is, it doesn't, freeze at the given liquidus point, it goes below that. And then if it suddenly solidifies, then you have carbide formation. So you have to reduce that undercooling and see that, at the eutectic temperature, the metal freezes. This is the main purpose of inoculation. By doing that, there is a uniform graphitization, and that helps achieve good casting. Can inoculation alone guarantee a shrinkage-free casting? Something Mr. Manish also addressed. Now, during solidification, volumetric shrinkage is bound to occur because of the austenite contraction. Now, that is why by altering chemistry, the graphitization potential, changing the solidification rate, we can avoid shrinkage. What does this mean? If you had only carbon, why don't we just melt pig iron and, form the casting? When there is austenitic contraction and volumetric shrinkage is happening, you need the right presence of carbon for the free graphite to expand and fill within this volumetric zone and provide you a sound casting. So how does that happen? By inoculation, which influences both the rate of solidification by reducing the undercooling. And how does it increase the graphitization potential? By improving nucleation sites. So by improving the nucleation sites, there are a lot of areas where graphite is going to expand, and the volumetric shrinkage that is distributed throughout is compensated by the graphite expansion and provides a shrinkage-free casting. So you need the rate of solidification, which can be done by your methoding, your chemistry, which influences the TL and the TE low, the liquidus and the solidus temperature also, and inoculation provides a nucleation site where the graphite sits and expands. So all these three in combination can only provide you a shrinkage-free casting. It's not just inoculation alone will not provide you the solution. There's a myth that gray cast iron does not require inoculation. Is it true? Because some people have been telling. No, because the manganese and sulfur from your base metal forms the substrate for the nuclei. But for this new manganese substrate to sit, it has to sit on a barium oxysulfide or a calcium oxysulfide or a aluminum oxide strontium. Above that MNS, and above the MNS is where your graphite locates and expands. So you cannot just feel that without any inoculation, I can produce gray cast iron. That is not true. What is silicon recovery from inoculation? Can it be used as a metric for inoculant effectiveness? So I'm giving you some various scenarios where a silicon percentage in the your inoculant is 65%, 70%, and 75%, assuming a uniform addition rate of 0.2%, and you get a silicon increase of 0.12, 0.13, and 1.4. So if you were to look at it, the first case, 0.2 into 65 should be 0.13. You have got 0.12, which means the recovery of silicon from your inoculant is 92%. So each case I have presented it. Now, in alloying, the method to increase silicon is by addition of ferrosilicon. You should not look at increasing your silicon from the inoculant and use that as a effectiveness for the inoculant. The purpose of the inoculant is to provide nucleation site. The purpose of ferrosilicon in the inoculant is the carrier for these elements like barium, calcium, strontium, which hardly take up more than 5%. So how would you add that 5%? You need a carrier. The carrier is ferrosilicon. Is over inoculation bad for the casting, and how? Over inoculation can lead to excess graphite precipitation, which can lead to mold wall movement. And you also have some special inoculants like bismuth and rare earth, which when they go into excess, provide you with detrimental effects of carbide formation or machinability issues naturally. Is high amount of pig iron addition in the charge mix good for the casting? So we have been doing some experiments, and what is the percentage of pig iron to use? So pig iron, when added in a specified ratio, is understood to improve the graphitization potential because of presence of elements like sulfur. That is the main thing it is coming. But a higher addition of pig iron may pose a problem of higher carbon. And if you must have a finer control of your carbon equivalent. Otherwise, this high carbon equivalent can give you lower mechanical properties. Also, there are other elements like titanium, phosphorus, which are present in the pig iron, which can affect the graphite shape and also result in carbides. Now, I see some shiny inclusions in casting. Are these dissolved enough? So these are some of the questions that rise up for the foundry man. Inoculants dissolve in the temperature range of 1150 to 1250. In the pouring process, the impact of low temperature and inoculant practice can result in incomplete dissolution, leading to localized concentration of inoculant. If that happens, you may see some shiny inclusion, but they are not necessarily undissolved inoculant. See, the way the alloying is done, a ferrosilicon-based inoculant should dissolve, and it's below the liquidus temperature of your chemical composition of the element of the metal you are pouring. So there is very small possibility of the inclusion being inoculant unless a non-suitable size is used. You use a very big size in a small treatment ladle, or you add it very late so that you don't, the temperature of the molten metal is at TL, and by the time you add the inoculant, it starts solidifying. Only in such a case it can happen. The composition of the ferrosilicon based inoculant is designed in such a way that it melts even before your TL, the liquidus. So here are some of the temperature. I'll just go back to it so you would be interested in this. So the barium based inoculant, the zirconium manganese inoculant, rare earth based, strontium based, bismuth based. We have taken these melting ranges based on the DTA analysis. Now next, what is inoculant fading and how do we address this? I think inoculant fading was also described by the previous panelist, even with a graph. Effect of inoculation is maximum immediately after the addition. Now, unfortunately, the fading of inoculant is also maximum immediately after addition. 50% of the the potency of the inoculation is happening very fast. So how you add the inoculant, what size of inoculant you add, the temperature at which you add, these are very, very important. All inoculants, all your magnesium alloys and ductile iron, they all fade. It is a characteristic. So it is in the process parameters that you will have to counter the effects of fading. Of course, if you look at a barium-based inoculant to a ferrosilicon with calcium and aluminum, barium acts when the temperature is above 1420, you have a pouring temperature, barium is effective. Below that, calcium is effective in forming the calcium oxysulfate. So to some extent, the composition of the inoculant helps, but the inoculation fading has to be jointly addressed with the process parameters. Now, can zirconium be used in both ductile iron? Because we have seen that being used in gray cast iron. Can it be done? When the base metal and other sources have low levels of zirconium, yes, then zirconium based inoculant can be used in ductile iron. We have seen ductile iron foundries using zirconium calcium based inoculant in their process. Since zirconium forms a stable nuclei, it can be used as a fade resistant inoculant. So barium, zirconium, strontium, they all form stable nuclei at a higher temperature. So just to give you, what is accepted limit then, because we have mentioned the base metal and other sources should have very low level of zirconium. So what is accepted level of each of these elements? So this is as per the ASTM, specialty handbook. You will find that zirconium up to 0.1% can be tolerated. So if it is within that range, you are having lower levels in your base metal and the other sources of your charge mix, yes, then zirconium can be used as an inoculant in ductile iron. What the right practice of addition to the liquid metal at different stages? Both the previous panelists had shown a pictorial diagram also of the various methods. So the inoculation addition to the stream of metal ensures better dissolution. And if you want, as I told you, fading occurs immediately after pouring. So the best way to have it is, either as an in-mold or as a stream inoculation. But there are different foundry practices. So a foundry which uses, ladle transfer and pours from the ladle directly into the molding box, mold through a monorail, they will be transferring metal to the ladle, and it is during this time that they add the inoculant. It is during the ladle transfer stage. They will have to add it when the ladle is 1/3 full and complete before it is 2/3, and then you give that balance 1/3 for a complete dissolution of the inoculant into the metal. And in stream inoculation, the rate of addition is to be maintained because excess inoculation can lead to undissolved inoculant. And that is why the size and the addition rate, you will see that it never exceeds 0.15 and very rarely it goes to 0.2%. Whereas when you do a ladle addition, it is 0.25 to even sometimes 0.3 to compensate for both your fading and the higher temperature at which you tap and the pouring line, the last box pouring. Inoculation should start along with filling and then along with filling of the mold. Start and fill, like this is your late stream additions. Can pure elements like bismuth, silicon, aluminum, zirconium, manganese be added as inoculant? Yeah, you said, like 5% is all this. Why can't I add them as a, pure metal? Then, can I save money? Now, any alloy has a lower melting point than a pure metal. So, which means a pure metal will have a higher melting point. Like I said, when we design the ferroalloy based inoculants, we see that, the melting point and the dissolution is lesser than your TL, so that we have a complete dissolution. Whereas a pure metal, you have no control. The way it occurs in nature, it has its melting point. So in some cases, it may have a higher melting point, and which will result in undissolved these pure metals, which can cause localized solidification, and around that you can have shrinkage or any other casting related defects. So it is always better to add any of the elements that are involved in inoculation as a alloy. So is there any criteria for inoculation selection in gray and ductile cast iron? Now this is going to be the last slide that I am presenting. We do have, based on the process parameters. So what are the process parameters? Your pouring temperature, your casting section thickness, your pouring time, and the composition of the metal. So section thickness, inoculation addition stage, pouring time, and tapping temperature. Based on this, what are the types of inoculant that you can add? Can you add a calcium based, or a barium calcium based, or a zirconium manganese, strontium based, strontium zirconium, lanthanum based, or aluminum based? So this is the chart that gives you which you can select. Next, I will give you the chart for the ductile iron. So here you have, the very thin castings, thick casting, thin and thick casting, because, it varies in the ductile iron. The inoculation addition, whether it's the first stage or the second stage, or is it in mold. The pouring time, you have a long pouring time, short pouring time, high pouring time, high temperature. The long pouring time is never more than 8 minutes. Okay, it is within that we define the short or the long. In tapping temperature, higher temperature, people doing pouring through the line. Sometimes I have seen, though we advise to keep within 8 minutes, some people pour for 10 minutes. So naturally they would like to up the tapping temperature so that there is no metal that is cold for the last box. Then your casting requirements, microporosity or nodal count, which is a very critical issue you are facing, and according to that, which is the inoculant you should select. Like the previous slides also showed, where you used a bismuth based inoculant, where you need a higher nodule count, you need a microporosity to be addressed, you use a lanthanum calcium based inoculant. So I have taken just some 12 questions that could pop up into the foundryman's mind as a frequently asked question, and try to address them. That brings me to the end of the PowerPoint presentation. Thank you all for the participation and listening, and I once again thank